welcome to the EMCH 362 Vardam Lab. I'm Frank Thomas, your TA for this lab, and so we'll go ahead and get started. So our lab objective is to characterize flow through a porous medium. What we'll be doing this with is resin flowing through fabric reinforcement to make a composite part. So the key element of this is our glass fiber fabric. That will be placing here on our tool surface or mold, and then we will be putting a distribution media on top of it, and that will allow the resin to flow through the part. And this process is called resin transfer molding, and the means by which we'll be having the resin moved is by means of a vacuum pump. So therefore, this is called a vacuum-assisted resin transfer molding, or Vardam for short. So now we know what a Vardam is. And so that'll give us a part that is relatively strong in tension and also in bending, because these glass fibers are relatively strong if you pull on them, but the moment you try to bend them, it just flops around. So the resin matrix, or really any polymer in most cases of composite parts, redistributes the load back to the fibers, even in like bending and compression or anything other than tension. So it gives us a much stronger part compared to something of like, or compared to similar weight, even of metal, and especially polymer on its own. So a few things we need to focus on for this lab are safety. So first of all, I am wearing gloves. These glass fibers are relatively inert, so it's not too dangerous, but even these do cause skin irritation because they're very fine and they may cause micro cuts. It's another industrial application of fiberglass is the pink insulation you often see in homes, though it's more of a omnidirectional. It's not as high strength or as consistently produced, but it is chemically similar and causes skin irritation for the exact same reason. Another thing I'm doing is wearing safety glasses because we are working with chemicals, including resin and other things like acetone and mold release, and those, when they get in your eyes, they don't have a good result. So I guess there's a few other things that we have here. We have cotton batting. That's called, we use this for what we call breather. That allows the vacuum, the air to flow through the part into the vacuum nozzle and into the pump. This bagging material here, let's see, it's just a polymer film, relatively stretchy. It lets us apply a vacuum down to the table and really suck down good. And this here is what we call tacky tape. It's just a sealant for the vacuum bag. As far as chemicals go, we have acetone for cleaning. We have mold release for making sure that the part will come off the surface once it's cured. And then we have parts A and B of our resin system. So once these are mixed, this is a fast hardener. So we have a very short amount of time to run the infusion before it has hardened. So we wait to mix these until we are ready to go. We have the vacuum pump. The vacuum pump's over here, and when we turn it on, it will apply vacuum pressure to the hose. But we actually have a stop in the hose where this goes to the vacuum pump, and this line goes to our part. And in the middle, we have a pot, and if the resin is pulled through the part into the hose, it will drop into this container. And the reason that is important is because if we have resin that gets sucked into the vacuum pump, well, really any liquid sucked into the vacuum pump would be bad for our vacuum pump, but a curing resin is possibly the worst thing that could get sucked into your vacuum pump. So therefore we have this resin trap. Also, it conveniently lets us monitor the pressure on the vacuum pressure on the part. We also have a gauge over on the vacuum pump itself, but this gives us gives a better indication as to what it is close to the part. Knowing the pressure on the part is important in our calculation for the amount of pressure and for the permeability based on the resin flow rate. So that'll come into play once we're running the experiment. We actually need to start preparing our surface for the experiment. First, we want to make sure that the surface is nice and clean. Probably want to come all the way to the edge. So to clean our surface, we use acetone usually. It's pretty harsh. Don't want to breathe this too deeply, and if you get it if you continued contact with skin, actually is a carcinogen. So making sure your gloves are intact while you're handling it is very important, as mentioned before. Once our surface is relatively clean and dry, this stuff dries off really quickly. We'll go ahead and apply some mold release. In a production part, you really ideally want to apply several layers of mold release. So the way that looks is you make sure that the entire surface that's in contact with your composite part has been covered with mold release. Then you give it some time to dry, and then you apply another coat. We'll just apply 2 coats here relatively quickly. We're actually going to go ahead and after the resin flow has been demonstrated, we will go ahead and quickly remove it before it cures. So that won't really be a problem for us. Disposable tape measure that will allow us to track the resin flow while the part is curing. So we'll go ahead and get started now that our surface is prepared. We'll go ahead and find the spot we want our part to be on. We want to place our breather such that it's very close to the part. If there's a gap like here, the bag could suck down, sealing off the part, and the part doesn't get the vacuum it needs. So we want the breather to be contacting the part. When you're manufacturing a composite part, generally you will leave a so-called sacrificial region that if the quality is not great, then you just cut it off and process the edge so that it's good and doesn't serve as some kind of pre-crack or something. So we're going to be putting a resin inlet tube on this end, but you'll be seeing that in a second. Before we do anything else, we want to surround the part with our tacky tape because we want it to be well sealed. Any vacuum leaks, in addition to not giving us the proper pressure we're expecting, which will throw off our calculation, will also allow air in the part, and air in the part during curing results in air bubbles, which turn into voids when the part is cured. And voids interfere with the matrix's ability to redistribute the load, therefore resulting in a weaker part. And we don't want any weaker parts because that is suboptimal. Even like Vardem is a relatively cost-efficient option for manufacturing composite parts, but it's not cheap, so we do not want to waste material. And if you're making a production part, you don't want to find out that your part was low quality when it's in use. So what I'm doing right now is I'm tearing at the lining here, the backing of the tacky tape, and that is letting me kind of steer the tacky tape. What you can also do is you can cut it off along each edge and overlay it. In fact, we have this joint here that is overlaid, but the fewer of these you have to deal with, the better it is for your sealing, because while tacky tape does seal to itself relatively well, it's still not perfect. And so if you have a continuous barrier, it's better than a discontinuous barrier. So I'm going to start this right here. This is where we will have our resin inlet tube. It's laying right on the edge of the part. Right on top we have our distribution media, and in a production part we'd also have peel ply in between the distribution media and the part. That would allow for easy removal of said distribution media, because this just adds to weight and does not add to strength, so it's effectively useless. What I'm going to do now is place a bit of tacky tape over top of this inlet tube. We want to kind of surround it, fill in little gaps around the bottom. So that the bag will lay right down on top of it, and we won't have to worry about too many leaks. We'll probably have to mess around with it. It likes to stick to gloves as well. We'll have to mess around with it a bit, but the less we have to, the better it is. Also, on this other end, I'm going to go ahead and put a pleat in. That will, because we have this kind of raised part here, we'll need a bit more bagging material. And so if you go ahead and put a pleat in, that allows for more material on this end as well, making kind of a tube. So all I do is take a small strip, this is probably even more than I need, and turn it in on itself, press it together so that it seals well, and then press it down on to the tape surface. So we're pretty close to putting on the vacuum bag, but first we want to note where our nozzle will be. And so overlay our film and make sure we have enough width on the edge, and we do. So now we just want to make a slight indentation. It's better than a razor knife, but those are in short supply currently, or at least good ones. But anything that will make a point will do. The less shearing in the bag you have, the better it is. Now I just have to lay it down on this, and then take it off the part before we start shifting things around in ways we don't want. Also, let's see where we put that. Oh, there it is. It's have a little O-ring here that lays over the bag. That kind of fills any gaps, ideally. And then this washer here, its nut tightens down. We don't want it too tight initially. We will tighten it down all the way before we start running our experiment. So now it looks like we're ready to start laying down our bag. So the center. Want to lay it down progressively. We don't want wrinkles. There are ways of dealing with wrinkles, but as you go, you don't want to press down too hard on it until you're sure that it is where you want it. We just remove the backing a little bit at a time. Tap it down. Look for any potential sites of wrinkle formation, and if you tap it down lightly, you can rearrange things a bit. Our distribution media is getting pushed around a bit. But then sometimes they like to stick to things a little bit afterwards. It's not quite the same as a fresh one, but it will do fine. So once you've got one side pretty good, you go ahead and start working on the other side. So that's fine. Like everything is about how we like it, so we can start kind of pressing down a bit. So far it looks like we don't have too many potential leaks. Looks like we're about ready to go ahead and start applying back. Got ourselves a pretty good bag. I'm gonna go ahead and try to stretch out and make this line here less prominent, because that's going to lead to a bit more resin than we like. It seems like the only source of the leak was, well, this needs to be tightened down, and then is pretty silent. That is the sign that your vacuum is fairly strong. And with our gauge, it is at full pressure. So, yes, we have about an atmosphere pressure on this, or 101.325 kilopascals metric. Alright, so now that our part is under full vacuum, we are ready to run the infusion. Last thing we will do before we do so is apply our measuring tape. This will let us gauge very precisely the amount of travel we see in our flow front. Let's see. So what we do is we pick a point along the width, and we use that to gauge the position of the flow front as a whole over time. Generally, we'd like to do it toward the center. Sometimes the flow front isn't very even. This distribution media is not quite straight, so it probably won't. Also, the position of the hose, but as the part's fully infused, it will be relatively consistent, even if it's not immediately so. So, now that we're ready to infuse, we can start mixing. So it's a 2-to-1 ratio of part 1 and part 2. So this is the resin, and then we have hardener. There are different kinds of hardener. The one we're using for this will be a fast hardener. That's good for smaller parts that you want to make relatively quickly. If we were making a real production part, we would measure this a bit more precisely, but for our purposes, we can gauge relatively well what 2-to-1 ratio is. And then we'll mix thoroughly and start the infusion. For a larger part, you'd want to use a slow hardener, because this goes through this polymerization relatively quickly, in half an hour. So you get a very small working time. So we just mix, scrape the sides and the bottom, so we get a very consistent look throughout. We try not to introduce bubbles. If you were running a slow hardener system and you wanted very good quality, you can even put a container, the mixed container, into a vacuum chamber, and that would suck all the bubbles out. So that means you get basically no voids, or much fewer anyway. So once the resin is appropriately mixed, as we believe it is, we're going to quickly place the resin inlet tube into the resin. Now we are recording the flow front position as it travels along. Starts out relatively quick, but then slows down. So if you watch the position over time, it looks relatively nonlinear, but at the far end, the flow rate becomes basically a straight line. So that will give you an effective flow rate. That seems like you're taking on some air. I don't know how that is. Must be a leak in the bag. than ideal, but it's good enough for demonstration purposes. But this data would not give us a very good result for permeability or flow rate. One of the downsides of Artem is that if you do develop leaks in the bag, it can cause problems like this. The vacuum does help to alleviate somewhat the effects of the air bubbles, but really the less air you have traveling through your part, the better. If it ever gets trapped in there, you have yourself a void. I'm really not sure where this is coming from. Oh. Seems to have slowed it. Anyway, that's about, it's nearly to the end, so we should probably go ahead and not go ahead and turn off the vacuum pump. A little bit of revenue, it's not up there to catch it. So we'll go ahead and take off the vacuum so that we don't get it in the line. But that is an example of a simple Vartum infusion. So the data we would have got from this experiment would have been the position over time, and that is what you'll be getting to run your calculations. So using Darcy's law, you can, and some doing a little bit of math, which we'll go over, you can basically take this flow position over time and estimate the permeability of the whole structure. And then from that, you can do basically a weighted average based on layer thickness to find the individual layer permeability. And the other thing that you'll be getting from this is the knowing the cross-sectional area. You can use this flow front velocity basically to estimate your flow rate. That'll be true for somewhere around here. Wherever it becomes linear, basically ignore this data, because the initial data where it's filling up really quickly, the vacuum pump isn't having to pull so much resin, so it goes fast, but then as it pulls more and more resin, it has to kind of, it goes into basically a steady state, and that's where you get an effective flow rate. And then so you'll individually calculate those values, and then you'll take the values for data set comparing like 6 and 8 layers, running in separate infusions, and then for that's just going to pull off the table if I don't stop it now. Based on that data, you can run a statistical analysis to see, are 6 and 8 layers significantly different? Is that true for effective permeability? Is it true for layer permeability? Is it true for effective flow rate? So that's some big numbers you'll be getting out of that. Good luck. Be sure to contact me. You'll have my info in the kind of the theory lecture that's being posted as well. If you have any questions, yeah, good luck.